Very much. I'll be talking about those encoding biases, influences on development and use of ontologies in the life sciences. The short end of it is that there are different ways of representing something in your ontology. We call it here for ease of reference a meaningful unit for various reasons that we will see. And at the end of it, it's that the conflicting requirements, they actually can't all be met in the same one type of ontology. So basically, if you want to achieve that, you're asking for the moon, and you may be close to it and you feel close to it, but it's not actually going to work. They have to balance certain different design requirements. So what are we talking about then in the detail? We're first going to look at some content and motivation. Okay, what are we talking about with representing something out of ontologies in a different way, so the encoding biases. Looking at ontology patterns, those are effects on ontology development. We go from patterns to styles in an ontology. And then we look at the effects in applications and how that affects your application design. And you may have had certain frustrations using certain ontologies for applications. And hopefully at the end of the presentation, you will understand and appreciate those better, which then in the end will help you to design better ontologies for the purpose that you want to. At least that's the idea for where we arrive at the end. So with the context and the motivation, ontologies, they used to be developed just for their own sake, just for having one or representing the information, and notably also for communication among humans. They have to stand closer to the thingy. Okay, sorry. So that's the hybrid thing, and I'm used to actually walking around rather than standing only with the microphone. Anyway, so ontologies for their own sake in the early 2000s, and for human communication, because in that way you could be more precise in representing what you're talking about. Over the years, it has been much more focused on, okay, we need to do something with the ontologies because people want to have a return on investment, basically. That's what it comes down to. Using it in ontology-driven information systems, for instance, for querying, data integration, linking, and natural language processing, you name it. There are applications for that for ontologies. And those different reasons actually may affect how the knowledge is represented in the ontology at the end of it. Historically, that is called encoding bias, and basically different ways of formalizing it. So that also means that it's separate from related but confounding factors. It's not about debating, are we going to represent concepts or universals in the ontology? That is assumed to be agreed upon. Or novice mistakes between subsumption and parenthood. We're also not talking about novice mistakes, we're talking about the case where the knowledge or the meaningful unit, the piece of reality that you want to represent in your ontology, you actually agree upon. And still there are differences in the way you're going to put it in your ontology. It's also not talking about interference of a cognitive bias, right? We're really talking about an agreement anyway. So they are differently encoded, as a term is used, as basically differently formalized for that. It was noted even back then, 25 years ago, but nobody really knew what to do with it. Over the years, over the development of a whole bunch of ontologies, we got better insight in it, and we started basically systematizing it to be able to properly manage it, because of my background in ontology engineering, and I want to be able to have a mechanism to manage it so that ontology developers will have an easier life in developing their ontology, basically. So for if we look at this whole notion of ontology development, there are several macro level methodologies, sort of like an information systems approach to developing the ontologies. And that can be a waterfall with iteration, that can be a life cycle, that can be something like the NEON methodology that drags in different kinds of reuse of resources, bottom-up methodologies, etc. They are high-level approaches. What we're looking at here specifically is what you could consider micro-level, or basically the ontology authoring, actually typing up those axioms into your ontology. And they use micro-level guidelines for that, such as OntoClean, OntoParts, and to help you to put those axioms in the ontology. There are other tools to help modeling, to debug, to integrate. And those encoding biases, they actually creep in at this stage. And this is the stage that we will focus on in the remainder of the presentation. So if we give intuitive examples for that, we know that the reality is the same, for instance, when a caterpillar transforms into a butterfly. But are we going to put this notion of transformation in the ontology as a class transformation that the caterpillar and the butterfly, the chrysalis and the butterfly participate in? Or are we going to make that into a binary relation and something transforms into something else? But we have the same notion of our butterfly and caterpillar. And we have what is the consequence of those choices, and yeah, what are the different options available there? Or take, for instance, an enzyme is a protein. Informally, we say so. But you also can say, well, no, actually the enzyme has as bearer the protein, or the protein bears that specific enzyme, a specific function or role that it can carry out. Same thing, same reality, different ways of talking about it, and different ways of precision. Mice and the colors, or any kind of object with different kind of colors, how are we going to represent that? Also there are different ways for that. Intuitively we knew this. What we're looking at now here is like, how are you going to systematize that? Comparing examples here as well, to if you look one step towards application, there are different intuitions on what would be nice in our ontology, or the shape of our ontology. In the top, you can see here a more precise representation that is basically biased towards a science focus, to be as detailed as possible as you can. Whereas in the middle, that is this more compact representation about the same information, about the same subject domain, or the same meaningful unit. It's much more compact. It's easier for your data sets if you want to annotate your data sets with a specific ontology. And at the bottom, you see another, yet another example in the same kind of area on the ventilators. And it's not ontologically very precise, but if you don't want to do precise things with it, say for instance, document annotation, it might be sufficient. So these are a couple of intuitive examples of what we're looking at when we're looking at different notions or different ways of representing something in our ontology. Key questions that arise then, because we know there are some of those differences intuitively, and they can hand wave to that. But what we really want to know is, okay, does it matter which way you represent it in ontology? If so, how, where, why? And would one way always be better than the other way? Could we be talking about a better way and an absolute case of that? Also the question, okay, which patterns are there actually? Because if you know which patterns are, you would be able to actually more easily choose on that one instead of trying to figure that out and bumping into it yourself. And those patterns, are they actually really equivalent or not after all on second investigation? And do certain patterns perhaps co-occur? And then if that is the case, then maybe they actually make up a style of representing something. You get a different kind of ontology. You can categorize your ontology for that. And then the question, okay, if you have answers to all of this, how does this affect the use and reuse of ontologies, given all of those patterns that are maybe there and the different ways to represent it? For ontology imports, foundational ontology you use, data integration, literature annotation, etc., and the way that we use ontologies. So let's look at those kind of things and try to answer those kind of questions. So first of all, when we look at those ontology patterns, we identified several modeling patterns, and here I'm going to show six of them, 6 categories basically of those patterns. They were collected from several sources, and summarizing them here. We devised also a formalization of it, so we can actually be precise about it. Once we have a formalization of those patterns, that also means you would be able to align those patterns and perhaps swap those patterns. If you have one kind of pattern and you want to actually have the other one, instead of manually doing that, maybe then we can automate that as well, because we have a formalization of it and then we know how to swap basically. And we then had also algorithms for designing for automated finding of those patterns and checking correctness. I will not focus on that last part here for this section, but we have some of that as well. So let's just see here that example that we saw for the transformation. Here actually what is going on. There are actually several of those ones. There's no issue to reify or not to reify a specific process or a verb, if natural language perspective. So that can be, for instance, here with the recursive relation, and we see on the right-hand side, we make there, instead of having a married to, we have a marriage and it involves 2 people. So there's also with polygamy, there's multiple cases where there are only two. You have no country, as far as I'm aware, where you can have a threesome marriage. But those kind of things you can then debate about, because you actually have to represent that kind of detail, because you did that as a consequence of representing it in that way. Here's another example that actually comes from the Buffalo ontology with the hybridoma cell line. Produces this monoclonal antibody reagent, as an example from that ontology. If you were to reify that, you get a class production with two participations in there, and also additional constraints. You can push this scenario up further to actually link it to a foundational ontology, rather than only reifying it. So you have different levels of making that more precise in much more detail. This then also gives two consequences and things you actually have to consider for which pattern you actually would want to choose. Are those more precise cardinality constraints actually needed? I think it's nice to have them, and it's nice to debate about them, what it should be, but do you need them? And that is not something I can answer. That is something you would have to answer for yourself when you're modeling. And then obviously you also have an additional question with the option B here, which foundational ontology are you going to align it to if you want to align it? Other one that is generally good for more debate is this notion of attributions, or informally also called attributes. There are two options here, so you have denoted that here is C and D. So for instance, you could have a person has skill, and could be a string. If you have a conceptual data model, like for instance a UML, and you just have a string and it could be a sequence of values. It's not the best way to represent it, also practically in databases neither, but you could if you want to. And it is nicely compact. Other option is that you say, well, no, we're going to bump up skill to a class. And we have a hierarchy of skills to be more precise about that and how many skills there can be. You see here also an attribute, but in this case, this kind of attribute is a different kind of attribute that we have here, because with the color, at some point, we're going to have to put more details in there about what that value is for that color and that color region. And then it also depends again on your foundational ontology. And there are just pros and cons for the data properties. Data properties themselves, as you see here, up here with string, and even there as an alternative way of representing it, it's an implementation choice. Ontologies are not supposed to contain implementation choices, because an ontology originally was intended to be used across applications. If you make your application an implementation choice, then it is tied to that specific scenario, and that makes your ontology less reusable as a consequence of choosing a data property with a data type. The other hand, obviously here, if you link it to a foundational ontology, in this case I use terms from the Dolce because it makes it easier to represent for this notion of the quality and the qualia. Then you have an issue, okay, how are we going to link that practically to our database? Because in the end, in the database, you have your data stored. And here, you don't have that sort of detail there. So, and then you have, yeah, the third component, as I mentioned already, is what kind of thing is actually hidden in the attribute to say, okay, what kind of pattern, as alternative pattern, do you have to actually remodel it? Other one, penultimate one, the rules and the subclasses, the protein and the enzyme that we saw beforehand. So here it's again drawn, we have all formalization for all these pretty pictures. I'm just showing you pretty pictures because people tend to like pictures more than a formalization of it. So you have here your subclassing, oops, wait, that was the wrong one. You have here your subclassing, or you have your bearer, as I mentioned before. Again, the foundational ontology approach is the one on the right-hand side, and you have to, again, the choice, okay, which foundational ontology you're going to use. Another design decision that is relevant here is this notion of property inheritance. Because on the left-hand side, if you give protein a property that has, for instance, a molecular weight and has a secondary structure, if you put that there on protein, it gets inhered into the enzyme, and we can have that information about the enzyme as well. And we get that for free. basically, purely by the principles and semantics of the logic and of the modeling language. Whereas on the right-hand side, we do not have them. So if you want to do something about enzymes and the molecular weight or the secondary structure, you're going to have to add something else to it. That blows up the amount of axioms you're going to have to put in your ontology. So that is something to consider, basically. I'm not going to say which one at the moment, not which one is better than the other one. That's partially a separate story. First, I list here the different options for that. Last one for here as examples. There will be more, but I'm just giving here just a general flavor of the issue at hand here, and a set that is fairly common, basically, that is recurring in a lot of ontologies. The popular alternative ontology patterns. I saw here that I made a typo. This is actually not test, but test status. So there are different ways to talk about values, the notion of the one-off construct in OWL, and the notion of subclasses. So for instance, if you want to see, okay, where does something, all of these kind of patterns appear in your ontologies? The one here on the right-hand side actually comes from the CEDO ontology, the coronavirus infectious disease ontology. The one here at the bottom comes from the CODO ontologies, also an ontology on COVID. They try to align it, and then you have to find a way of, okay, one has it in this way, the other one has it in that way. How are you going to solve this? So that's why it's like they are actually concrete cases, all of them, but this one. People like to hear about the COVID stuff, so here is one of those examples. So same case here, what is I have this issue with data properties on the left-hand side there. Again, that is an implementation decision and an application decision rather than having something generic and reusable. Then there is another thing that creeps in here as a discussion, is this notion of should you have individuals in an ontology at all, or should it only be type level information? And further on, this notion of one-off nominals, ontologically, it's very awkward. And if you add one test status, whichever it may be, that means actually that the meaning of the class test status actually changes. Whereas if you had that here on the right-hand side, that kind of modeling is much more stable. You just add one more subclass, but it doesn't fundamentally change what you have been representing. So in that sense, you have certain pros and cons to different patterns for that. Other thing, but maybe that modelers don't care too much about, is that this one is much more computationally, much more costly than the other two options. But yeah, and that has to do with scalability for that. So how are we going to manage its patterns? The first thing I've mentioned is we're going to formalize this. So there's a language of patterns instantiation, there's a language for patterns themselves. And then each pattern has certain, like of the metadata, like a pattern name, the elements, the axiom components, and a full formalization. So here, this is a very basic idea shown here. Let's say, for instance, a basic all-sum ontology pattern. You have a name, you have the elements from our vocabulary from the pattern language. It's basically in a meta level for that. It's not necessarily an ontology design pattern, it's just a pattern. It's not necessarily that you want to design it in this way. You have your axiom components, the full formalization, and here you would have an example instantiation of that specific all-sum pattern. And we can do that for all of those patterns that we saw on the previous slides, which we did, and the references mentioned there. And the key thing here is we look here as an example for this case A, and we're not going to go through all of them because that would be a bit boring, but I will give you one example here. Just to see the difference in the amount of axioms that are needed. So the pattern A, what we had on the left-hand side with this person married to another person, or this hyperlysed cell line produces this monoclonal antibody agent. That is just these two axioms, and you sort it, basically. The one that we had on the right-hand side, the written out one, is these axioms and all of these axioms that it actually costs to represent it in specific detail. So if we then look at where does it matter, now that we know that there are a bunch of those patterns, and it may make it easier to select one, but where would that actually have an effect when you design your ontologies? It has to do with ontology interoperability and alignment, Because if you have two ontologies and one uses one pattern, the other one uses the other pattern, what are you going to do? Are you going to re-engineer that one ontology to be able to reuse it, or maybe you're going to make a heterogeneous alignment? And if so, how are you going to manage that one then? So that is also your ontology reuse. It also affects ontology development to help that for those tools that actually aim to help you adding those axioms to the ontology, because they then have to guide you which kind of axioms you're going to put in there. And it also has an effect on the deployment, but that we'll see in the next subsection. So to give you an example where certain aspects of ontology development will affect which pattern you may end up with, for instance. There are NLP-based approaches to do term harvesting. What kind of terms you're going to need in your ontology? You take a corpus of scientific literature, you see which terms and which verbs appear, and then you're going to want to put that in your ontology. The thing there is, with a typical approach, you get a proliferation of candidate object properties. And it is based on the mistaken belief that each verb matches to a specific object property. But generally, we have the same kind of relations and different ways of talking about it. So what you actually would need to do is separate the language layer from the ontological layer and choose one name of a relation that maps to multiple verbs that you harvested from the literature. But yeah, you get that kind of draft ontology basically for it. Similar case for if you take conceptual data models, or if you have databases and you want to extract content for your ontology out of it. What you do is you're reverse engineering from your tables to a very flat structure. You may, based on the data, find certain relations, but then you get still a very flat structure. And that is the foundation, basically, of relational databases. They are called relational for a reason. But with that kind of flat structure, again, you get a lot of those candidate object properties, and you get a flat structure which is not interesting for automated reasoning, so you will not be able to find mistakes in that way, because it won't be able to derive much for that. Another one, if we look at something that has finally become somewhat popular, is this notion of using competency questions and defining competency questions to be able to demarcate the content of your ontology. Then you develop your ontology, and then the idea is you test your competency questions against the content of the ontology to see if you developed at least something that was within the scope of what you initially specified. The initial approaches for that was basically a slot-based approach that you see here at the top, which sees class expression, object property expression, another class expression. They were so-called archetypes. And they were assumed to map to exactly one type of axiom. So this is an axiom type that it would link to. So if you have this kind of pattern in your question, you would put that kind of axiom into your ontology. And it was just a one-to-one mapping for that one. And one-to-one mapping of the term for this one to the term that you put in your ontology. And when we were working on test-driven development, we stumbled into the fact that it wasn't actually working like that. So basically, what actually is the case that for the same question, there can be and has been modeled differently. We collected all of those competency questions, which are from the specific ontologies, from the literature, looking at those ontologies, how did they implement that kind of stuff that from that competency question, how did it appear in the ontology? So we looked at that, and then it turned out there is actually an end-to-end relation between the competency questions and the axioms that we have in the ontology. And it also means there are different requirements on the queries, the Sparkle out queries that you have to formulate to be able to check your ontology on whether that competency question has been satisfied, basically. So we use in that case rather entity chunks and predicate chunks. Also here in this case, separating the ontology, the axiom layer from the linguist and the language layer for that. Because you had to, because there are different ways for that. So I have here an example from concrete cases from our data set. So there was the same pattern, what you see here, EC1, PC1, EC2. And here's just an example of four of the questions that satisfy that specific pattern that we had found from all, and basically analyzing all of those competency questions. Same pattern, but there's actually different ways how it ends up in the ontology. So what data are measured for gate assessment is just a simple all-sum construct that we saw. And there you have this nice one-to-one mapping that we saw on the previous slide. The other three, no, they're doing it differently, even though that our competency question has the exact same pattern. What is here with the second and third one is from the software ontology. You have your binary relation, also in with the all sum and the all sum, but here the task X and here this the dedicated physical activities, or i.e. exercises, actually had to query for a superclass in the hierarchy than a simple all sum construct. And it also means that in the end, your queries are going to be different. And if you then know which pattern maps to which subset of queries, then at least we can give you a query pattern to check for, instead of you having to write and figure out how to formulate a Sparkle Out query. If you stick to one of those patterns that we saw from the question patterns, we can say, well, select one of those subtypes for subtypes variants for Sparkle Out queries. The last one here has it as most expressive in a way. So that what software can read a cell file actually was separated out into two binary relations and the constraints on the range of the last one. And they are all the same questions, so that you can see even the same piece of information, different ways of formalizing it. So that is summed up here with the formalization options. Now that we know that from the data, we actually can help start helping basically the ontology developers. Look, if you have this kind of questions, choose one of these kind of patterns for the axiom patterns to put it in your ontology. And correspondingly, we then have basically a query signature that will help you testing that competency question in that ontology in the way that you have formalized it. We did that first with a competency question template language. We're working on finalizing that whole pipeline basically for that. So the first part is already there. And what to do with all of those differences, and you already can see it's going to have some effect on the ontology development tools. You want to maybe swap one for the other, one pattern for another pattern, heterogeneous alignment as mentioned. In any case, do not put both in your ontology because you want to please everybody. We have seen some of those ontologies as well when we were analyzing it, so don't do that. Choose just one and stick to it. Whichever you choose, use it consistently throughout your ontology, because then we can go to the notion of ontology styles. And if you have a certain subset of patterns that you use consistently, and then you get one style of an ontology, then if you want to go to another style, we just make transformations from this pattern to that pattern, and then you can get a whole different style of ontology, but you can only do that if you have that consistently throughout your ontology. So what does it mean when we talk about the style of an ontology? That happens if those decisions are made systematically throughout. Not that you choose one transformation of and the other one, if it's not a class transformation, in other case, a member of, for instance. You either reify all of those ones or you don't reify all of them, for instance. So once you know those styles, you can develop those converters. But then you need to know what are those styles. Can we actually identify styles in the ontologies? What does it mean to have a style? What are the dimensions contributing to a style? What are the parameters, values, variations to choose from to actually come to the notion of a style? So we looked into that one as well. To make a long story short, just to clarify, we're talking about a style. Eventually, we had a notion of representation style or modeling style. Is a set of features used for representing a particular piece of conceptualization. For those people who want to represent conceptualizations or reality or understanding of reality, we don't care for that one. We have a general definition. for which there may be different, meaningfully equivalent, but not necessarily logically equivalent ways to represent it in a logic that supports that particular style. And the representation style is a justification-based positive design decision in at least one scenario. So we're excluding what is called anti-patterns, so like bad ways of representing things. Yeah, there is a motivation why you put it in there that will give you a benefit in some way. That's the key point of that last part. So we did an inventarization of that. We ended up with 10 dimensions with 28 traits. I'm not going to go through all of them, but just to give you a flavor of what kind of things are there. So for instance, theoretical, you can say when there is a degree of adherence to ontological principles in representing something. Like for instance, we have seen this reification of processes. That is more a theoretical based approach to your ontology development. This notion of qualities instead of attributes. The notion of inherence of roles and no data properties. Whereas on the applied side, you would get predominantly or entirely those sort of more applied decision, implementation, application decisions in there, such as those attributes or data types, processes as data properties, and processes as relations for that rather than a reification. I can say in some cases you have a mixed bag in a specific ontology that, I don't know, maybe different people represent it in a different way and use a different approach to representing something and they put it together in one ontology. And you may want to clean that up in the end. Related to that is also what a theoretical, this notion of the granularity of relations. You have your parsimony, say for instance, only 10 relations in the relation ontology and you have to deal with that and all of the relations are only any of those. Or you have this notion of abundance with refinements on the basic relations, but then domain-specific relations you would want to add to it. Engineering aspects that have an effect as well. Monolithic ontology, you have a modular ontology that can be modular externally or internally, where you have, for instance, in a way you have a big domain and you carve it up into different modules. Or you say, well, no, we have ontology and we import a specific module, or a different approach of ontology design and how you put your ontology together, basically. The GCIs I'm going to skip because nobody is really using them, but as just mentioned there, I already give the answer away there. And then we have this thing where it comes back as another example for where we saw different patterns with this notion of this nominals and the one-off versus the subclassing and the notion of classes, instances there. But we saw with the example with the test status as well. This one is a similar for that. And then the question was, after this kind of inventarization, we had this longer list, are they actually operationalizable? Can you use that? When you have a set of ontologies, can you figure out, are there ontologies that actually stick to one of those styles? Or can we not really use it anyway? Because if you can use it, then it's nice, and then we can take a next step in our ontology engineering approach. If not, we have to go back to the drawing board and figure out something notion of the styles, because intuitively it was there. So yeah, in the end, we did that with a bunch of ontologies, and there is indeed a difference in how the theory-oriented ontologies are shaped as compared to application-oriented ontologies, how they are shaped. So we put it nicely in a spider dynamic diagram. I can go back there and see because spot the differences there. In some with respect to the differences, what we find interesting is that what is informally known as a foundational ontology like Sumo actually has all the characteristics of an applied ontology and not actually really of a foundational ontology or theory-oriented ontology. There is no reuse of relations typically with this hierarchy, bare or flat kind of structure that you have of your ontology, and that matches quite in a quite regular way how conceptual data models look like ER diagrams. You see that actually reappearing as certain things that are out files that are called ontologies. And it's indeed the case that our applied ontologies have more use of nominals, instances, and data properties. I would say these are key aspects of the observations, but we indeed can identify the different modeling styles in the different ontologies for that. And then you could say, well, look, we have all of this theoretical stuff. Does it actually matter in practice? And the answer is this. We have seen an example on the ventilator there as well with the different purposes at the start so far. We have seen this aspect from the competency question to axiom, the ratio that is end-to-end rather than one-to-end. This notion of ontology reuse that I touched upon, I have more information about that if you're interested in. I'm not going to talk about that here. And you can choose an encoding bias for a purpose and choose a style to fit the purpose of what you want to achieve. But they also promise something on how does it affect actual applications in the life sciences. So we're going to look at that one. So one is one that actually, from the moment that I saw it, was really nice. Is what is called an intelligent textbook called Inquire Biology, developed by SRI. The idea was to annotate a textbook with the ontology that was developed for that specific textbook, and then you can annotate it with those ontology terms, and then you can generate questions automatically and mark them automatically. And who wouldn't want to have that, especially in all this remote learning that we have to do with ever more students and fewer academics. So here is a picture of that, what they did. They had a textbook, in this case was for Campbell and Reese's textbook. You see that here, hopefully you can see it at the back. It comes out better in color here than it comes out better here. So here you see something in yellow. And there are terminology used here that is actually also from the ontology. And then you see on the right-hand side, it generates questions based on the content in the ontology. So an example here, also from that paper that I redesigned it a little bit to make it look pretty, is, for instance, you see here a little section of that ontology. And you can then generate the question based on the knowledge represented. What is the relation between a carbohydrate and a biomembrane? Those terms come straight from our ontology. And then the answer can automatically be generated purely by using verbalization of ontologies, the axioms basically, because we have our path here and just verbalize the path, and that automatically can give our answer. Carbohydrate side chain is a carbohydrate, that is our subsumption here. That is part of a glycolipid, that is part of a biomembrane. And then that gives some notion of active learning to the student as well. So that looks nice as an application of life sciences. So then we're like, okay, we want to have that too, but not just for just having their application where the tag is closed. We're saying, okay, how can we generalize this? How can we build something like that works for any ontology? And then if somebody else solves the problem of annotating a textbook with the terms on the ontology, we can do this too, but then not for one tailored textbook or one tailored ontology, but the generic case. So we designed question templates for that, for 10 different educational questions. So here are 2 examples given, again, separating the language layer from the ontology layer. And we had a notion of axiom prerequisites, which axioms have to be present to be able to formulate that question and to have that we have that answer in our ontology so we can generate the answer. And what we already saw there is that it assumes actually a certain way of representing your information in the ontology. Specifically, the applied option. Basically for the content that is being generated, because you want content about that specific subject domain. You don't want questions about endurance and dispositions if you're learning about cell biology. You just look at the proper domain. You want to have this abundance of relations, because then you have a much more larger variety of formulating those questions, and much more precise questions that can be formulated, and much more precise answers that can be generated. So that already gives an indication there is a difference there on what is good for what kind of ontology you would need for this kind of application scenario. So here, to give that as an example, we have our hybridoma cell line again. Sample formalization thereof, and we can generate those pretty questions. This monoclonal antibody reagent produced by some hybridoma cell line, and then we'll give an answer yes, because we have that in our ontology. So all fine and all good, we get this working in that way. However, If we remember that alternative pattern that we saw, where we reify the relation, like we had the reproduction here, besides that we get more axioms here, if we use the same approach with the axiom prerequisites, we get one of those ugly sentences like, what does a cell line participate in? What does it participate in? It participates in a production. That's not what you want in your question generation. It's ontologically much more precise, but it doesn't work for this kind of application scenario. The minimum what you want to have, and you can't see that now because of the thingy, but you would have to have a production of monoclonal antibody reagent. That's at least a little bit better, but not as pretty and not as clear. Oops, not as clear and pretty as this one up here. And basically in an applied way of representing it. That's fine, I can deal with it. But the only way to get rid of it is stop sharing. So I did that also with about 8 ontologies that we tested with in different kind of ontologies to see, okay, what is the effect? And not just with one ontology, but we want to have the generic approach. So here are some of the other sentences. They are correct. They are grammatically correct. They are semantically correct, but they are not questions for students you want to give to the students. Like it does a material object project onto an immaterial 3-dimensional physical entity. But that's content from Bio-Ontologies and the foundational notions of biology, and because it's a core ontology there. And that's a similar case. It's the other one for Bio-Ontologies and the staff ontology, but I know I have to move on. The other thing what we had there as a notion is the naming of the entities in your ontology. There is an old naming process to put the name of the thing that is on the right-hand side in the range in the name of the object property. But if you then take the name of the object property and you stuff that into the verb position in a sentence, you get all of this repetition. So then you get, does a mixed stuff has a part stuff that is a stuff? It's correct, but it's not nice. So and there were more of those kind of things with the naming for that kind of naming, as well as this notion of naming in context. So you have the pizza ontology, and when you see American as a subclass of pizza, you know that they mean American pizza. But if you have that class separately, un-American, nobody knows what un-American it is. You actually would have to name that thing in the ontology that says American pizza. So you had that contextual issues we had with it as well for that. So yeah, that's the same thing what I mentioned here already. But it doesn't mean that for all applications you want to have this applied approach. So here we have one about cell type ontology. It uses this kind of more generic approach, and here they call it the capable of relationship. For instance, you have the Kupffer cell, and the liver is capable of some erythrocyte clearance with the main range independent continuant and buffer process. So you have that sort of like this more theoretical representation. That's capable of is used over 1,500 times. So there is loads and loads and loads of detail in that cell ontology in representing that specific way. So we see that here as, but here at the top, that is sort of like the generic pattern that they are using. If you were to use the abundance relation, the abundance of relations approach, they all would be looking like something like these ones. If you have the examples, I'm making either the red ones. I'm making up now. They don't have that in the ontology, but if you had the abundance relations, that is what you would need, which is an option. But you only can see there are loads and loads of relations. So I was then thinking, okay, how is it going to have an effect on how they are using the cell ontology? So in the paper from 21 that I was just cited there, there are the list of 10 applications that they use. And I was hoping to find something. The sad thing is, however, is that those applications only use term search. So you have all of this detailed information in your cell ontology, and it is not used in the applications. But if you were to, and you would want to do more advanced searches with it that you can do with the ontology, like a function or the role of a specific cell, the data sets for an experiment or on erythrocyte clearance, for instance, by macrophages. Those questions you can formulate with the ontology. And in this case, this approach which they're capable of is much easier than if you were to have this abundance of relations. Because if you're an intermittent user, you will not know all of those abundance of relations. You do not know what to ask for. Whereas one simple capable of, that's easy to manage and easy to handle. So in that sense, it would be actually easier to work with for that. And as last example, before closing, I still have time for 5 minutes. Okay, cool. So as last example, this notion of ontology-based data access that you may have heard of, using the terms of the ontology to be able to query the data in the databases, so you can query it at the what layer rather than at the how layer. And that is based on this preliminary from the mid-90s, how the computer scientists had envisioned that thou shalt use ontologies. I know the gene ontology took a whole different route for it, so you may not everybody may be familiar with it. But the original idea from the computer science perspective was that you have your databases here at the bottom. There is somewhere conceptual data models, maybe all in ER, or maybe some in ER, some in object role modeling, some in UML, whichever mixture of it. And it is the ontology on top of that. They are one layer above this conceptual modeling. That is the one that provides the structured controlled vocabulary, where you agree on that when we use the term flower here, is the same as the flower in the other model and the blommages in the third model, whichever language you use. It doesn't matter because you map it all to flower there, and that provides the agreement. So that was the original idea in the 90s to solve that, because there were loads of data integration issues, because there were loads of companies merging, and they had to do all of this data integration with the databases. So all fine and well. Then they came with the idea of, look, it would actually be nice to query on the data that people don't need to know how the data is stored in the ontology, just the what. So it basically only queries over the ontology and abstracting away from all of this implementation stuff that end users don't want to know about also either. So here's one example of a possible architecture. There are several of those architectures around. The essence is that you have something that works with an alt file, you do your management, you play around here at the knowledge layer, you link it in some way to this data layer where you have your data stores. There can be a relational database, RDF stores. You can even store it in JSON if you want to. And there is a link between the two up there. In this case, it's a transformation. What we see here then is that you have this idea of ontology at the top, with some formalization behind it, but we can give it a pretty picture as syntactic sugar. You don't have to deal with the formalization. We transform it to the abstract relational model to a relational model to a database. And then you have this sequence so that if you use terms from the ontology, we know where exactly in the database it is. And we have automated algorithms for that. You can do that with the transformation. You can use ontology-based data access that uses a mapping layer. It doesn't matter. They're going to have the same problem with respect to the modeling, the way of modeling stuff in your ontology. So the OBDA uses a mapping layer for the terms in the ontology with a query over the data. You can represent it in sort of like an ontology graph-like way. You can represent the same stuff also in your ER way. So actually what we did there with the ontology-based data access is conflating this notion of ontology with what we normally had in conceptual data models. Basically what we have is a formalized conceptual data model and not an ontology proper that was originally intended for integration across applications. How does it have an effect on querying? So we have here, select one example there with our flower and a color. If you then want to query something like, give me all the red flowers, just as a very simple example to fit it on the slide. Graphically, we have a tool for that as well. You can click on what you want to do. And then if there is any constraining value, like for instance red, you fill that in and it will translate this pretty picture into the logic, from the logic to the query over the database, and it fetches it and it gives you the answer automatically. So this is nice and neat and small, no, but that is our applied way of representing something. if you do that the foundational ontology way, we get all of this extra stuff. And this extra stuff clutters the visuals, which is not nice for the end user. And computationally, it actually has to manage all of those kind of things in answering the queries and translating the graphical to the eventual SQL query as well. So that takes up a lot more time, and then it's not really reusable in the end anymore. We tried and it didn't work, and we have to do certain back-end optimizations. So in this case, actually, what we end up with is that for something like ontology-based data access, you do not want and you cannot actually properly have a theory-oriented ontology. And you need to have your applied style, which is de facto technically in conceptual data model just formalized and all. Mainly just domain and range axioms that you're dealing with rather than all of those details that we saw before. In this case, however, the ontology naming, vocabulary naming is not an issue for that kind of application scenario. So to sum up, to have enough time for discussion and questions, those encoding biases, they do exist. We have summarized here, it's those 6 groups of it. They combine into styles that we have evidence for that as well. Affects ontology development, it affects from bottom-up ontology algorithms to competency question management, to verification of your ontologies. It has an effect throughout those kind of things from ontology development. And as you may have seen, it affects ontology use as well. Will not resolve itself automatically, but it needs better management with tools and methods and techniques. I have those key questions answered here that we started off with. But what I think may be more interesting to close off with is certain considerations to what is interesting for discussion on this issue. Those encoding biases, as mentioned, it affects usability and reusability. If you have the downside, if you have your applied style with application decisions, defeats the original purpose of the ontology. But it's so much nicer in applications in most cases. If you have your theoretical style, that is all nice in theory and good principles, and then you will have a better reuse of your ontologies, but it makes it harder to use it in applications. And you have those conflicting requirements, and there is actually no good solution to. So, and again, then there's the other thing, when maybe we have to be mindful of the purpose of the ontologies and sometimes not conflate other artifacts like conceptual data models or thesauri as ontologies, because they interfere with this notion of ontology style as well. There are various things we can look at what to do. Maybe we should adjust modeling languages for the modeler's own good. I know it sounds a little bit condescending, but maybe we should remove the data properties from OWL to make sure that people don't use it, because ontology are not supposed to have that. But then you can say, well, no, we want to have this for the applied reason. So that is something you may want to discuss and debate about. Systematizing categories of ontologies. Maybe you could force the ontology developer to choose their categories, make a commitment, stick to it, instead of the freedom. But you know, some people will prefer the freedom, so you may want to discuss about that as well. Maybe there's also a case of better educational materials, and the alternative is from the ontology engineering side. Okay, maybe we just should patch it up with guidelines, methods, and tools to mitigate the worst, to make it not too bad for the ontology developers themselves. So they are things you could think about, like collaborators, funding. And thank you very much. I have that textbook here. You can freely download it as well. And if you would want to know how I ended up from microbiology, getting a PhD in computer science and all of that sort of stuff, and the piece in development in between, that one is described here in the little memoir. Thank you very much. Oops, that's the wrong direction. Backup slides.
All right, we'll start with an online question, if that's all right. Sorry. So from Robert Hohendorf, he asked, one criterion mentioned in the talk is how hard it is to use ontologies in applications. I wonder if there's a theoretical framework to assess and possibly quantify this hardness. How is this currently measured and assessed?
Currently, it's not measured and assessed. What I presented here is basically foundations that we want to try to be able to assess that. And that this notion of defining styles is a step towards actually helping to get to that point that we can, in the end, we can say, we can automatically analyze the structure of your ontology and say, well, look, if this is that structure, you want to do that with it, you're going to have to re-engineer it. And that we can say that purely by analyzing your ontology. So yes, we want to get there, but we're not there yet, because you can see that would be useful for ontology developers themselves. And yeah, these are steps basically towards that goal. Thank you.
Any questions from the audience in person?
Well, actually, a related question, I guess, and what are the barriers to creating those methods and implementing them in the tool? Do you have more thoughts on that?
Time, funding. No, so okay, that is definitely a key one that has slowed down the progress from this work, and in this case, because you can see some of the papers there from 2019, and not a lot has happened there. For the competency questions, we have made progress there because you need to take one thing at a time, and so for our side, we did it. It's basically we investigated the mappings. And our collaborators look at more at okay, how can we generate more of those the queries? How can we manage that one? And then we need to combine those things together. So we basically take one thing at a time. The barriers at the moment, I would say it's the investigation, getting more data. I have a student working on the swapping of the algorithms. So he designed the algorithms and they're implemented, but we don't have that in a pretty end user tool just yet. Because in the end, from the ontology engineering side, we cannot say you must choose this one or you must choose that one. We only can say, well, look, if you want this, you're going to have to do it this way because that we already know is not going to work. But that is the best we can do in that sense. And those conditional statements, in a way, they still have to be, I would say, in detail done and made pretty for a wrapper around it, basically. But yeah, that's more the end user style of it. So yeah, it's largely the amount of people and the amount of funding to be able to actually continue further with it. So yeah, if there are more people interested, we'd be happy.
Any other questions?
So I have actually maybe one thing adding to that is in some cases, as I mentioned earlier, we have seen ontologies that can't make up their minds which style they would use, and they use a little bit in one section, they use this way of representing thing and another style in another part of the ontology. So from our perspective, it would be helpful if you just use one style and stick to it, and one kind of pattern of representing something and use that throughout. That makes it easier to manage computationally, because that makes the algorithm easier to deal with, because we know what to search for. And even finding sub-ontologies or modules within the ontology is not a trivial exercise from a computational perspective. So that would help if we would reduce that. So in that sense, I mentioned somewhere on the slides this notion of better educational material that we hope that might help as well, that people know upfront which one to choose for, and that would make our algorithms and our life in that sense a little bit easier to get you those supporting tools faster in a way.
I have a question, but there's no. Okay, so what if I want to put multiple ontologies together and they all use different styles? What do you recommend if you're in that situation?
So we have that in that other paper. I had some backup slides for that. We have this notion of heterogeneous alignment. So here is the formalization of it. What I had in the previous slide is only up to here, with the different patterns. So say when this is half a line and we have here 1.5 line. But we have there as well, okay, how can we align those patterns? Because in some cases you can modify the other ontologies, in some cases you cannot. So if you cannot, then you have to have something what we call a heterogeneous alignment. we have the formalizations of that one as well. Now for a heterogeneous alignment, it's generally composed of a combination of homogeneous mappings between the same kind of things, between one class and one ontology and another class and the other ontologies. And then we have some heterogeneous ones there at the bottom, so that you can match those things. So right here, we have a pretty picture as well with the heterogeneous alignment. Not a bio example, but an example with just tennis ontology and a sports ontology as a generic case. Where you see here, you have your Olympiads with your sports, you have a tournament and a tennis player, and you have here the alignments, the subsumption here and that subsumption there. And then with those heterogeneous alignments, because those ones are essentially alignments, what we can compute is that this thingy, this reification there amounts to the same thing what you have over here. So that you can do with the heterogeneous alignments, if that's what you need. Maybe it's not what you want because it makes things a little bit more complicated, but it is possible to do so. The other option is if you can modify the other ontology, and I have one student finishing up on that, is basically instead of saying we align it, we're going to say we're going to swap this thing for that thing or vice versa. So currently we only do it from the complicated to the simpler way because we assume and hope, and based on a theory of designing ontologies, that you have your generic theory-oriented ontology as the principal thing that you start with, because that will work across applications, and that you just make different application versions of it. And then you go basically only from this expressive one to the shorter one, because that is easier to do and easier to manage, because then we don't need input from the end user. Because otherwise we have to say, okay, which one, with all of the extra things here need names. If you have, so that person, are we going to say, okay, the transformation is obviously an easy word, but there are different words you can call the reified thingy. And then you can have, and you have to add the constraints to it, and you have the interaction with the user. So it's easier to go from, in that regards, from the complicated theory one to the simpler one for that reason. And for the theoretical reason, you're actually supposed to do the theoretical approach first, and then different applications, different modules perhaps that you only need for it. And then you can swap if you can modify the other ontology. But yeah, that depends on who is in charge of the ontologies. Or maybe you say, well, look, we don't care. But if you say we're not allowed to modify, we're going to take it, we're going to modify it anyway. Whatever you can, it's up to you to choose. But yeah, those algorithms and implementation we have at the moment. Yeah. So we're getting in that sense to it step by step.